When people hear that a new liquid hydrogen project has been announced, they usually imagine one company designing the facility, building the infrastructure, installing the equipment, and ultimately producing the hydrogen. From the outside, that assumption seems reasonable. After all, press releases often highlight a single developer, a single operator, or a single technology company. But the reality is dramatically different. In fact, one of the biggest misconceptions in the hydrogen industry is the idea that any single company builds an entire liquid hydrogen plant. What you are looking at here is one of the most complex industrial systems ever created. Every pipe, every valve, every compressor, every refrigeration system, every storage tank, and every control network originates from a different part of a massive global supply chain. Some companies specialize in compression. Others specialize in cryogenic refrigeration. Others manufacture pumps, instrumentation, valves, insulation systems, storage tanks, electrical systems, or automation platforms. A liquid hydrogen plant is not a product. It is an ecosystem. It is a collection of hundreds of specialized technologies working together with extraordinary precision. And as governments and industries invest billions into hydrogen infrastructure, understanding who actually builds these facilities is becoming increasingly important. Because behind every hydrogen plant is a hidden network of companies that most people never see. This is the industry's biggest secret. Behind every liquid hydrogen facility lies a hidden network of specialized suppliers. Most people see the finished plant. They see the storage tanks, process units, and loading terminals. What they don't see are the hundreds of companies that supplied the technology required to make the facility operate. A liquid hydrogen plant is similar to a modern passenger aircraft. The airline may own the aircraft, but thousands of companies contributed to its construction. The same principle applies here. Compressor manufacturers provide the equipment that increases hydrogen pressure. Heat exchanger suppliers provide cooling systems. Cryogenic specialists design refrigeration technology capable of reaching temperatures colder than almost anywhere found naturally on Earth. Tank manufacturers create storage systems capable of maintaining liquid hydrogen at -253 degrees Celsius. Valve companies develop specialized flow control systems. Instrumentation suppliers provide sensors, transmitters, and automation networks that monitor every part of the process. EPC contractors then bring everything together into one integrated facility. The final plant may look like a single project, but underneath the surface it represents an enormous collaboration spanning multiple countries, industries, and decades of engineering experience. Without this hidden supply chain, liquid hydrogen simply would not exist. The journey begins with compression. Hydrogen gas occupies an enormous amount of space under normal atmospheric conditions. Before it can be cooled and transformed into a liquid, it must first be compressed to much higher pressures. This may sound straightforward, but hydrogen compression is one of the most demanding applications in industrial engineering. Hydrogen molecules are extremely small. They can leak through seals that easily contain other gases. They can diffuse into materials. They can contribute to hydrogen embrittlement, a phenomenon that can weaken certain metals over time. Because of these challenges, hydrogen compressors require specialized designs, advanced metallurgy, and extremely precise manufacturing. Companies such as Atlas Copco, Baker Hughes, and Siemens Energy have invested decades into developing equipment capable of handling these conditions. As hydrogen enters the compressor, pressure increases through multiple stages. The gas becomes denser and more suitable for downstream processing. At the same time, engineers must carefully manage temperature, purity, reliability, and efficiency. Any contamination entering the system at this stage can create significant problems later during cryogenic processing. That is why hydrogen compression is not simply about increasing pressure. It is about preparing hydrogen for every step that follows. Compression forms the foundation of the entire liquefaction process and establishes the conditions required for efficient cooling and liquefaction. Once hydrogen leaves the compression stage, it carries a significant amount of heat. That heat becomes a major obstacle because the next stages of the liquefaction process require extremely low temperatures. Before hydrogen can enter the cryogenic refrigeration system, engineers must first remove as much thermal energy as possible through a process known as pre-cooling. This is where massive industrial heat exchangers begin their work. Hydrogen flows through carefully engineered pathways while cooling media absorb heat from the gas stream. The objective is simple: reduce the refrigeration burden later in the process. The engineering challenge, however, is anything but simple. Engineers must optimize thermal performance, pressure losses, operating costs, and equipment reliability simultaneously. Every degree of temperature reduction achieved here translates into energy savings downstream. This is why pre-cooling systems often operate as some of the most important efficiency enhancers within a liquefaction facility. Companies specializing in heat transfer technologies contribute highly sophisticated equipment capable of handling demanding industrial conditions while maintaining precise temperature control. Although visitors rarely pay attention to these systems, they play a critical role in determining overall plant efficiency. Without effective pre-cooling, the energy required to liquefy hydrogen would increase substantially. In many ways, these heat exchangers quietly determine whether a project becomes economically competitive or struggles with high operating costs. Hidden behind pipes and steel structures, pre-cooling represents one of the industry's most valuable but least visible technologies. Now we arrive at the most extraordinary part of the facility. Cryogenic refrigeration is where hydrogen begins its journey toward temperatures colder than almost any naturally occurring environment on Earth. Liquid hydrogen exists at approximately -253 degrees Celsius. Reaching that temperature requires an engineering achievement that few industries have mastered. Inside the massive cold boxes shown here, hydrogen passes through an intricate network of heat exchangers, refrigeration circuits, expansion devices, and cryogenic equipment. Each stage removes more thermal energy from the hydrogen stream. As temperatures fall, the engineering becomes increasingly difficult. Materials behave differently. Thermal contraction becomes significant. Small inefficiencies become expensive. Precision becomes absolutely essential. Specialized suppliers have spent decades refining technologies capable of achieving these conditions safely and efficiently. Every component inside the cryogenic refrigeration system must operate flawlessly because even minor disruptions can impact performance across the entire plant. This stage also consumes a substantial portion of the facility's electricity. In fact, one of the biggest challenges facing the hydrogen industry today is reducing the energy required for liquefaction. Engineers continuously seek more efficient refrigeration cycles, better heat integration strategies, and improved process designs. What makes cryogenic refrigeration remarkable is that it allows industry to create temperatures only a few degrees above absolute zero on a commercial scale. Without these systems, liquid hydrogen would remain a scientific curiosity rather than a practical energy carrier. After compression, pre-cooling, and cryogenic refrigeration, hydrogen finally reaches the moment that defines the entire facility. The gas undergoes a phase change and becomes a liquid. This transformation is one of the most important events in the hydrogen value chain because it dramatically changes how hydrogen can be stored and transported. Under normal conditions, hydrogen occupies enormous volumes. As a liquid, its volume shrinks dramatically, making large-scale transportation practical. This is why liquefaction is considered a critical enabling technology for future hydrogen trade. Countries with abundant renewable energy resources may eventually export liquid hydrogen across oceans in much the same way liquefied natural gas is traded today. However, achieving this transformation is incredibly challenging. Every step leading to this moment must be executed with extraordinary precision. Temperatures must remain stable, hydrogen purity must remain high, refrigeration systems must operate efficiently, instrumentation must provide accurate measurements. The phase change itself may appear simple from the outside, but it represents the culmination of one of the most sophisticated industrial processes ever developed. What you are witnessing here is not merely cooling. It is the conversion of hydrogen into a globally transportable energy carrier. This capability opens opportunities in heavy industry, transportation, energy storage, aerospace, and international energy markets. The liquid produced at this stage becomes the foundation for an entirely new energy infrastructure. Creating liquid hydrogen is an extraordinary achievement. Keeping it liquid is another challenge altogether. Once hydrogen has been liquefied, it must be stored in specialized cryogenic tanks capable of maintaining temperatures near -253 degrees Celsius. Even the smallest amount of heat entering the system can cause hydrogen to evaporate. This phenomenon, known as boil-off, represents one of the industry's most important operational challenges. To minimize heat transfer, engineers use advanced insulation systems, vacuum spaces, multiple containment layers, and specialized materials. The inner vessel holds the liquid hydrogen, while the outer structure provides mechanical protection and environmental isolation. Between them lies sophisticated insulation technology designed to slow the flow of heat into the tank. Every detail matters: the shape of the tank, the materials selected, the insulation configuration, and the operating procedures all influence performance. Modern cryogenic storage systems represent decades of accumulated engineering knowledge and continuous innovation. Without them, liquid hydrogen could not be transported, exported, distributed, or utilized effectively. These tanks may appear simple from the outside, but they are among the most advanced storage systems in the energy industry. They allow hydrogen produced in one location to be stored for future use, transported to customers, or loaded onto specialized vessels for international trade. In many ways, these storage tanks act as the bridge connecting production facilities to the broader hydrogen economy. At this point, the true story begins to emerge. Every major system we have explored was supplied by different companies. Compression equipment comes from one group of specialists. Heat exchangers come from another. Cryogenic refrigeration systems are provided by entirely different organizations. Storage tanks require their own dedicated suppliers. Control systems, instrumentation, electrical equipment, pumps, valves, and safety systems each originate from separate areas of the industrial ecosystem. This is why no single company builds a liquid hydrogen plant. Instead, these facilities are assembled through one of the most sophisticated supply chains in modern industry. Hundreds of suppliers contribute technologies that must work together flawlessly. Engineering teams coordinate designs across multiple countries and time zones. Manufacturing facilities produce equipment years before startup. Logistics providers transport oversized modules across continents. EPC contractors integrate everything into one functioning system. The final facility becomes a physical representation of global industrial collaboration. This hidden network is rarely visible to the public, yet it determines the success or failure of hydrogen projects around the world. As hydrogen investments continue to grow, supply chain capability may become one of the industry's most important competitive advantages. The companies supplying critical equipment are not simply vendors. They are the hidden builders of the hydrogen economy. The complexity of the supply chain creates an important vulnerability. A single missing component can delay an entire project. Imagine a liquefaction facility nearing completion. Foundations have been poured. Steel structures are in place. Piping systems have been installed. Electrical infrastructure is energized. Storage tanks are ready. Yet one critical cryogenic compressor has not arrived. Suddenly, progress stops. Commissioning schedules slip. Startup dates move further into the future. Financing costs increase. Revenue generation is postponed. Investors begin asking questions. This scenario is far more common than many people realize. Long lead time equipment often represents one of the greatest risks facing major hydrogen developments. Some specialized components require months or even years to manufacture. A delay at one supplier can ripple across the entire project schedule. Because liquid hydrogen facilities rely on so many specialized technologies, supply chain resilience becomes just as important as engineering excellence. Companies that secure equipment early often gain a significant advantage. Developers increasingly recognize that project success depends not only on technology and financing, but also on supplier relationships and procurement strategy. As the hydrogen industry scales, bottlenecks could become one of the defining challenges of global deployment. The hidden supply chain that enables hydrogen growth can also become the factor that limits it. The future of hydrogen may ultimately depend on one question: can the supply chain scale fast enough? Around the world, governments, utilities, industrial companies, and investors are planning massive hydrogen projects. New facilities are being proposed across North America, Europe, Australia, the Middle East, and Asia. Demand for compressors, refrigeration systems, storage tanks, valves, controls, and cryogenic equipment is expected to grow significantly over the coming decades. This growth creates tremendous opportunities, but it also places enormous pressure on suppliers. Manufacturing capacity must expand. Skilled workers must be trained. Engineering expertise must grow. Production facilities must increase output while maintaining quality and reliability. The challenge extends far beyond simply building more hydrogen plants. The challenge involves building the industrial ecosystem capable of supporting them. History has shown that major energy transitions often depend on supply chain development as much as technology innovation. The same appears true for hydrogen. Success will require coordination across equipment manufacturers, engineering firms, project developers, governments, and investors. If the supply chain scales successfully, hydrogen could become a major component of the global energy system. If it struggles, deployment could be slower than many forecasts suggest. Either way, the companies supplying the hidden infrastructure will play a decisive role in shaping the future of hydrogen. If there is one lesson from this journey, it is that hydrogen projects are far more complex than they appear. Behind every facility lies an enormous network of technologies, suppliers, engineering disciplines, and industrial systems. Understanding these systems is becoming increasingly valuable as hydrogen moves from demonstration projects toward large-scale commercial deployment. That is exactly why H2 Hub by Renee Energy was created. H2 Hub is a learning platform designed to help professionals, students, engineers, developers, and investors understand the technologies driving the hydrogen economy. From hydrogen fundamentals and electrolysis to fuel cells, storage systems, compression technologies, liquefaction processes, project economics, and infrastructure development. H2 Hub provides practical knowledge focused on real-world applications. The goal is not simply to explain hydrogen. The goal is to explain how hydrogen projects actually work. As the industry continues to grow, those who understand the hidden systems behind the headlines will be best positioned to identify opportunities, evaluate technologies, and contribute to the energy transition. If you want to deepen your understanding of hydrogen infrastructure and the engineering that powers it, visit H2 Hub by Renee Energy. Because the future hydrogen economy will be built by people who understand the systems behind it. And those systems are often hidden in plain sight.